You have a quantized large language model running on a forward, deployed server with no uplink. It has been processing sensor fusion outputs and generating targeting recommendations for 90 days. No telemetry has come out. No model updates have gone in. Today, someone asks whether the model is still performing within acceptable parameters. The honest architectural answer is you have no mechanism to know. That question, and the silence it exposes, is the flaw this diagnosis is about. Standard MLOps architecture is built on 4 implicit assumptions, none stated in the design docs. First, the model registry is reachable. Every inference server expects to validate its running version against MLflow, SageMaker, or equivalent. Second, telemetry is continuous. Drift detectors, SHAP collectors, and latency histograms stream back to a central aggregator in near real time. Third, the feature store is live. Inputs join against current data, not 90-day-old snapshots. Fourth, the update path is automated. A retrained model clears validation gates and CI/CD pushes it within minutes. Each assumption encodes the same requirement: bidirectional low-latency connectivity to a cloud-hosted control plane. In a SCIF, aboard a vessel in emissions control, or at a forward operating base, all 4 collapse simultaneously. The architecture was never designed to survive their absence. Here is what actually happens when you impose the air gap. The inference server starts up. It checks the model registry, no root. It fails open, running the model version it last loaded from local disk. That version may be 3 releases behind. The monitoring agent attempts to push inference logs to the telemetry collector, no root. It drops them. Drift accumulates in silence. The feature pipeline tries to refresh the input feature store, no root. The model now operates on data that is increasingly stale relative to the distribution it was trained on. At some point, a critical vulnerability is discovered in the serving framework. The security patch exists. It cannot be delivered. There is no authenticated update channel. Someone physically carries a USB drive if they carry the right version at all. The flaw is not that air-gap deployment is operationally difficult. The flaw is that the MLOps control plane was designed as a single, monolithic, always-on dependency. When it disappears, nothing inside the inference stack has a graceful degradation path. The system does not fail safe. It fails silent. Put concrete numbers to this. In a connected deployment, model drift is detectable within an hour via population stability indices computed against a live baseline. In an air-gap deployment with no local monitoring stack, drift goes undetected until human evaluation, which in operational cycles may not occur for weeks. Model update latency in a connected pipeline with automated CI/CD runs under 30 minutes from validation pass to production. Via removable media with chain of custody handling, the same update takes days to weeks depending on logistics. Security patching follows the same curve, with vulnerability windows measured in weeks instead of hours. Quantization introduces a third constraint. A 70 billion parameter model at BF16 requires roughly 140 gigabytes of VRAM. INT4 quantization reduces that to around 35 gigabytes, but requantization and validation requires the original weights pipeline, which lives in the connected environment. The edge node cannot reconstruct its own model. The architectural correction is to decouple the inference stack from the control plane and rebuild local analogs for each failed assumption. Model governance moves from a remote registry to a hardware-rooted local registry. Cryptographically signed model bundles, versioned by hash, loaded only if the signature validates against a device-resident key. The update mechanism becomes a signed, offline deliverable package, prepared in the connected environment, transported via removable media, verified on arrival by the local governance layer. Telemetry moves from continuous streaming to store and forward. Inference logs buffer locally in a tamper-evident append-only store, synchronized back to the central aggregator when connectivity is restored. Drift detection moves from cloud-based population comparisons to local statistical process control, control charts, sequential probability ratio tests, and Jensen-Shannon divergence computed against a frozen baseline embedded at deployment time. None of these are as capable as their connected counterparts. They are, however, operational when the link drops. The proposed architecture does not assume connectivity. It treats connectivity as an optional enhancement layered on top of a self-contained inference governance stack. Name what this costs. The local governance layer adds 8 to 15 milliseconds of overhead per inference call for signature validation and telemetry buffering, acceptable for most batch or near real-time applications, prohibitive if you are operating under a 20 millisecond hard latency ceiling. The local telemetry buffer is a new attack surface. 90 days of inference logs sitting on a forward-deployed node represent an intelligence collection target if the hardware is captured. Store and forward synchronization, when connectivity resumes, creates a data exfiltration risk that requires careful classification of what gets buffered at all. Local drift detection without a live baseline carries a higher false positive rate. Thresholds must be tuned aggressively against the deployment distribution before fielding. And the signed update pipeline requires a key management infrastructure that most programs of record do not have funded. This architecture solves the technical problem. It does not solve the programmatic one. Every MLOps assumption is a hidden connectivity requirement. If you have not written down what your inference stack does when the control plane disappears, you have not finished the architecture. The question is not whether the model runs in the air gap. The question is whether you can govern it there. If the answer is no, you have not deployed a system, you have deployed a timer.